Okay, so so I heard a lot of exotic things today. So I apologize because I will talk about something that is much less exotic. It's just simple black holes with an event horizon and nothing around. So, but what's going on? Oh, okay. Let me go. So the point is, even if you just have a black hole in vacuum, you can still have modification to your theory of gravity, so you can still have deviations from the predictions of GR. But so I sort of work on the interplay between the theory and the astrophysical side. So my interest is to understand whether we can detect and actually whether we can identify these hypothetical modifications or not with different experimental setups. And in this case, I will talk about this experimental setup, which goes under the name of black hole spectroscopy. So it's not, okay. Okay, so this is just to point, right? It doesn't change slide. Okay, great. So, when you want to probe gravity with gravitational waves, there is this nice plot that you can use to understand which kind of gravity you are probing, which has the field on the x-axis, sorry, the potential on the x-axis, and it has the curvature scale on the y-axis. So it shows you that if you want to probe a strong gravity regime, you want to be in the top right corner of this diagram, where you are in the situation of strong potential and strong curvature. And if you look at it, you see that the experiments that allow you to probe this gravity region the most are ground-based gravitational wave experiments. And the reason why the ground-based are more powerful than space-based in this respect is because the curvature scales as inverse powers of the mass. So of course, if you have a stellar mass black hole, you probe higher curvature than a supermassive black hole. Now, and the same for other compact binaries, including neutron stars and binary black hole neutron stars. So, and if you look at the catalog of, this is a nice periodic table of the gravitational wave detections so far. The quasi-totality of them are binary black holes. So from which, I mean, we can do population inference, we can deduce that binary black holes will be the primary candidate of ground-based gravitational wave detectors, present ones and future ones. And binary black holes will be the systems that I will focus on. And so, okay, quickly, this is the anatomy of a binary black hole. You have the in-spiral, the merger, and the ring down, and you can use each of these phases to test gravity in a plethora of ways that have been explored by the LIGO-Virgo collaboration so far. No deviation from GR has been found. I don't know if I have to say that this is likely or unlikely, but anyway. So there are different tests that you can do, and the test that I will focus on goes under the name of black hole spectroscopy, and it focuses on just the tail of the waveform, which is the ring down part of the waveform. So let me just quickly describe the connection between having a ring down and being able to test gravity. So the ring down is just the output of the fact that the remnant relaxes towards equilibrium. It emits gravitational waves in the form of a superimposition of damped sinusoids, and they are characterized by frequencies and damping times, and they are the quasi-normal modes of the black hole. And why do you want to test gravity with this prediction? Well, first, one aspect of gravity that you want to test is the uniqueness theorem, which tells you that if you have stationary black holes in GR, they are uniquely described by the Kerr spacetime metric. Okay, this is a standard prediction of GR, and so okay. In the case of the ring down, sorry, yes. How does this translate when you look at the ring down? It translates into the fact that you are assuming that the output of the relaxation is a Kerr black hole, which goes under the name of a Kerr hypothesis. And I would say that this is a strong, it's a robust prediction of gravitational wave astronomy, that you have to asymptote to a Kerr black hole after the relaxation. And then when you perturb a black hole, another key prediction is that you can derive a master equation for the perturbations, which goes under the name of Tucholsky's equation. And so you will emit, so if you perturb a black hole, you will emit a train of waves in the form of ring down waveforms with characteristic frequency spectrum. So again, now, if you put all these things together, you will discover that frequencies and damping times, while formally they are infinite, but in reality, they are not independent from each other, but there are only two independent quasi-normal modes quantities. Either you can choose them as the frequency and damping time of the most dominant mode, or two frequencies or two damping times, whatever you like. But once you have determined two quantities that, of course, in general are the frequency and damping time of the dominant mode, in principle, if GR is correct, you already have determined all the others, which is why you can test GR. This is a key prediction of general relativity, and this is what you are going to test with this test based on black hole spectroscopy. So now this is not, I mean, this is not a new thing. It's been around by, I would say, 20 years. So you have black hole spectroscopy, which is a more general program which goes beyond testing GR, which is the program of measuring the frequencies and damping times and measuring this spectrum. And then you can do whatever you want then, but people like me would like to test GR with it. And then and then what do you do? Which kind of test do? You check that there is no third or fourth, fifth, nth independent frequency and or damping time in the spectrum. So one thing to take I want to highlight what you are really testing. You are testing the combination of two hypotheses. The first is that the remnant will be a Kerr black hole, and this is the Kerr hypothesis. And the second hypothesis that you are testing is what is the dynamics that governs the perturbation of the remnant, how you are approaching the remnant. And even if the remnant, you can have situations in modified gravity in which the remnant will still be a Kerr black hole, even if the underlying theory of gravity is not GR, because these theories, they still obey the uniqueness theorem. But the way of approaching towards the remnant will be different in any way. So even if you have the uniqueness theorem that is satisfied in your modified theory of gravity, you will still have deviations in the spectrum. And this is why you can use this formalism and this setup to test gravity. So now, where are we experimentally in this context? We are very far from black hole spectroscopy. So there has been only in this paper, there is no consensus about the results of this paper in the literature. They claim that they have detected a subdominant quasi-normal mode, so that they have detected the dominant one, and the dominant one has been detected for a lot of events. It has been measured, the properties have been measured, but up to now, there is no consensus on the detection of a second quasi-normal mode, which would allow you to start testing GR with black hole spectroscopy and starting to enter the era
you said which are they besides 150914 and this one 190521? Are there other events for which the dominant mode has been seen?
So I mean, if you sorry, in all these papers here, they do black hole. I mean, they. Yeah, you have to take a look. Yeah, but you're right that for many of them, the SNR in the ring down part of the waveform is quite low. But even for 150914, the SNR in the ring down is not 20. I mean, it's like 8 or 9.
They should find no deviation, whether they measure something in the test.
Well, actually, one of the things that they do here, they do parameter. Well, actually, what they actually do, they assume that there is at least one dominant mode. Then they do the parameter estimation. Then they assume that there is a second mode. Then they do the parameter estimation. They check for the bias factors, and 100% of the times they find that the bias factors, they favor the hypothesis of only one mode. Okay, so you're saying this is different from just computing bias factor. Okay, maybe we. Yes, we were here. So, but even assuming that they are correct, so this shows what you would typically do. You would identify the dominant mode, which is this mode here in a space of frequency and damping time. Then they claim we have identified another peak in the posterior, and this is compatible with the existence of the so-called 3-3 mode. So they say we have detected another quasi-normal mode in the spectrum. As I said, there is no consensus, but let's even assuming that this is correct. So you see what are the typical uncertainties in this parameter estimation. In the damping time, you are basically not measuring it at all. You have uncertainties that are order of 100% in the deviation. This is delta. So you have to imagine that if this number is equal to 1, it means that your relative deviation from GR is constrained to 100%, which means it is not constrained. And here, but this is a general fact. In general, you don't expect damping times to be very well constrained, but you expect frequencies to be much better constrained. These experiments are much more sensitive to frequencies. And so in frequency, you do a bit better in the sense that now you are constraining it at the 10% level. But I wouldn't say the 10% level, it's a big constraint that you are putting to GR. If we deviate from GR at the 10% level, we will see it already, and probably we would have already seen it. But if we didn't see yet, we will see with the next run. So let's say 10% is a very large constraint, or at least this is my opinion about it. So then we recently with Shweta Bhagwat, we did this experiment. We wanted to understand what SNR is required to detect a deviation from GR in the spectrum, which is at the order of 1%, not 10%. And we found, well, first let me state the result, and then there are some caveats in this result. But we found that you need an SNR that is larger than approximately 200 if you want to detect a 1% deviation from GR with a single event. So by an individual measurement. Then of course, then you know when you do tests of GR, you stack many events. But we here analyzed the simple situation of a single event, what SNR you need, and you need SNR 200, which means that at least for individual events, you will not be able to constrain GR at the percent level with present GW detectors. So there are caveats that are especially interesting for theorists, because actually, in order to simulate a deviation in the spectrum, we had to work with what is available in the literature, which is not much. So it's very challenging to compute spectra in theories that are different from GR. In GR, you can do it, and it has been done, and so we know what is the spectra, the spectrum of quasi-normal modes in GR. In beyond GR theories, we don't. So we have the only full case in which the people can do the computation, and it's non-GR is almost GR. It is Kerr-Newman. So it is GR plus an electromagnetic field. In all the other cases, they can only do computations perturbatively in the spin. This paper that came out recently by Lorenzo Pierini and Leonardo Gualtieri is the first example in which they do a second order perturbation in the spin. In all the other cases, you only have a first order perturbation in the spin, which is very far from a realistic situation, because in realistic situation, you will have remnants that have spins of the order 0.7, 0.8, 0.6. So you are very far from the realistic astrophysical case, but this is all that we have in the literature. Now, recently there was a paper that I still have to digest, honestly, but in which they claim, it is a very long paper, it's like a 50-page paper, but they claim that they have at least reduced the problem to a very general master equation that works non-perturbatively in the spin.
In terms of technical, you change the process to modify gravity, and then you look at the possibility of doing computation.
So in technically, okay, I can comment, but I think Paolo is much more expert than me in these technicalities. But basically, the technicality is the following. So if you are in GR, you can reduce the problem to a single master equation by a very clever manipulation due to Tucholsky. Yeah, which is something that in general you cannot do in beyond GR theory. So you have a plethora of coupled differential equations, which make the problem very challenging. In the case of Kerr-Newman, in the case of Kerr-Newman, they could do it. So after many years from Tucholsky's, but they managed to reduce the problem to a smaller set of differential equation. No, but it's a no, but it's fine. That's what I wanted to say.
You can also do it so you can your equations are not separable, but you can redefine your your eigenfunctions order by order, so that you end up diagonalizing. And you have one master equation. So you can do it generically to make any background, which is close to.
Well, who does this? Okay, so who does this? So who does this? Okay. But okay, I'm sorry if I missed the reference. No. Okay. But so it's similar to Kano. Okay, no, I'm sorry, I missed the reference. No. So okay, so we used what we had, and we see that the spectra that are available, we also considered simple spectra that we call delta-like and delta 220-like, which we just modify in a rigid way the frequencies of the spectrum, and we already see that the spectrum, that the available spectra, they branch into two types. And there are the good ones and the bad ones, let's say. And the bad ones that are the ones like Kerr-Newman, they are very degenerate. Even if you have SNR 1000, you will not be able to tell the difference from GR at a sensible level. But then there are the good ones, which I think are the ones that are more similar to what we believe modified gravity looks like. Then in this case, if you are at SNRs at around 200 or 300, then yes, then in this case, you can say the difference between GR and non-GR. Then we have, then this means that we have to go for third generation detectors to have at least a hope to identify modifications in the spectrum away from GR. And the reason is that you will have an improve of a factor of 10 in sensitivity. Then there is all this excitement that we will see black holes at large horizons for basically most of the astrophysical allowed range of black hole masses. Then I will show that for spectroscopy, this enthusiasm for horizons is not very well justified. But for the full signal, it is. Anyway, yes. So you don't have to. I think you don't have to oversell your expectations. It's true that I mean, this is a nice plot from the Cosmic Explorer. Is a planned third generation detectors in the US, and they have a very nice horizon study with this nice plot that shows the horizons up to which you can detect your sources, but it also shows how many sources there are differentially in the redshift. The redshift is represented as the radius. And so you see that in the region that we have explored so far with LIGO, there are not many sources in relative terms, I mean. So there are probably many sources in absolute terms, but not in relative terms. Most of the sources are here at redshifts larger than 1. And this is because of basically you can trace back this to the star formation rate. You have more star formation rate at high redshifts where you expect most of the sources, but high redshift means high distance, which also means that you expect most of the sources at a very low SNR. And I will show this like quantitatively in a while. And this already rings an alarm bell in our mind. I mean, it's true that third generation.
Which is the damping of the power, let's say this way.
The SNR goes inversely proportional to the distance, like 1 over the distance.
Okay, and the ratio of the distances? With what we are looking at and what.
So now we are looking at like we are looking at about what 500 megaparsec, and then while most of the sources will be, I don't know, at 10 gigaparsec, for example.
Okay.
And so what we did in collaboration with Paolo Panish, Shweta Bhagwat, and Michela Mapelli, we wanted to understand if we have a catalog of a realistic catalog of binary black holes, which has been obtained from a population synthesis code from Michela Mapelli. Can we simulate doing black hole spectroscopy on this catalog, and can we check, for example, how many events you will have with large SNR, how many events you will have with small SNR, and okay, but beyond the SNR, can we check how well we will be able to measure the subdominant quasi-normal modes in the spectrum? Because this will really tell you how well you will be able to constrain gravity with third generation detectors from spectroscopy alone. Then, of course, there are other tests of GR. They might be better than spectroscopy. I'm not claiming anything in either direction. I'm just restricting to spectroscopy. And then in this catalog, there are a lot of sources. So you have order of magnitude 10 to the 5 events per year, which doesn't mean 10 to the 5 events detected per year, 10 to the 5 events in total per year. And the catalog is, it has a total duration of 10 years. So we have a total number of sources, which is about 10 to the 6. Of course, we do not do Bayesian pipelines. We are using an approximation, a very common approximation that is that is the Fisher approximation. It would be impossible to run Bayesian pipelines on these catalogs. So, but basically what we find, if we consider a single Einstein telescope detector, we find that depending on the design, we find that we can detect at a low SNR, we can detect between 5,000 and 10,000 sources. But if you want to check how many sources have SNRs that are larger than 50 or larger than 100, very few of them will have per year. I mean, you start from a catalog that has 10 to the 5 events per year, and you end up with only 30 to 70 events per year that have SNR larger than 50. So this is an incredible damping. It means that the number of loud ring down events that you will see with third generation detectors in proportion will not be large, but I mean in absolute terms is still a good amount of events to test GR. Okay, since I have only 5 minutes, I will skip this slide. So this is telling you that with Cosmic Explorer, the situation improves dramatically by a factor of 10, basically. Now you see that you have between 16 by a factor of 5, actually, between 15 and 250 events per year with ring down larger than 50, and for ring down larger than 100, you have tens of events per year. But individually, there are some individual events in the catalog for which you even reach SNR up to 1,000 or almost 2,000. So now if you look at this, so as a reference, I took the ability of measuring the deviation in the 3-3 mode, in the deviation in the 3-3 mode. And so what you see is that if you want to check how many events are able to constrain this mode from GR at the 10% level, you have a lot of them. I mean, like 2,000 to 4,000, depending on the design. And even at the percent level of measurability, you have order of 10 of events if you combine ET plus CE. So what you can do, if you do a back of the envelope stacking calculation, you see that you will be able to constrain GR at the sub% level, which is, yes. No, okay. Now this is, you're right. So we are working on a follow-up project in which we want to check what is the optimal, the optimal stacking procedure. Now this is just, I'm just basically scaling by 1 over square root of n, which is not the correct way of doing it. It will be suboptimal. You're right.
You will lose the signal.
You are right. So if you do
one event with high spin and all other events are spinless, and you stack the posteriors together, you'll suppress the signal. You'll not see the signal.
You're right. No. You're right. Stacking is a highly non-trivial operation.
It depends on your assumptions.
You're right. It's a highly non-trivial operation. If you have a deviation that is not constant and is very sparse, then probably in this case you should introduce, I don't know, like selection effects, similarly to what they do in population
you should use a hierarchical.
Yes, you should use hierarchical
analysis, but then it depends on what hyper distribution for your.
You're right. No. You are absolutely right. So I am claiming this as a back of the envelope number, but I am actually working on a follow-up which is more rigorous, and we are trying to use hierarchical stacking, but we are seeing this sort of problems that you are talking about. That if you naively take all the sources and you stack them, you basically, even if you assume that the underlying theory is not GR, you cannot see it because the deviations is not present in equal. And then it's not trivial. So we thought that it would trivially work at the beginning, but actually it doesn't. So we have to work more tough on it. Then yes, finally conclusions. Yeah, I mean, this is general optimistic, self-motivating things that the 3G detectors will see a lot of things and with very high SNR. But so no, I think that the important takeovers are that if we manage to get a synergy between the Einstein telescope and the Cosmic Explorer, this would be the optimal situation in which we will be to test GR with black hole spectroscopy, which is okay. I mean, this will depend on political issues probably, and not only on scientific ones. And then, but the point that one should push for this synergy, from at least from this spectroscopy point of view, is that you will be able to probe GR at the sub-percent level. And as Enrico was saying, but then at the end it depends on which mechanism is modifying gravity. But in the most naive ones, you would be able to constrain a GR at the sub-percent level, which is much better than current detectors will do. And then, of course, it depends on the theory. I mean, if you have a theory that predicts a deviation from GR that scales as the Planck scale and goes, it suppresses GR by 10 to the -6, then okay, you have to build 5G detectors, not a 3G detector. But then we don't know. Actually, we don't know if GR is modified, and if it is, how. So we have to push the limits of our measurements because of, I mean, to understand it. Thank you.
Further questions? Comments?
So you explained the difficulties about measuring experimentally, observationally the cosine modes. But since I'm a theoretician, more theoretical oriented, I was curious about what you say at some point, that it is even difficult to predict, to compute theoretically the spectrums of the quasi-normal modes in modified gravity theories. So I ask you also, other here, whether one could say that developing new numerical methods or analytic characterization for quasi-normal modes is an important problem for this.
I agree.
Yeah,
I think this is one of the main problems in the community. If we had quasi-normal modes computed non-perturbatively for different theories, we could make more robust prediction. Like, for example, this prediction that I showed, that you need SNR 200. I was using and extrapolating the spectra that exist so far beyond their actual regime of validity, because the regime of validity is not astrophysical spin of 0.6 or 0.5. So you're right. This is an important problem that must be faced. But I don't know if Enrico wants to add, since I was not aware of. Oh, okay.
More questions? Okay, we thank the speaker. Yeah.